of like they say that it's good to take like the SAT 2 times. It's kind of good to see what the AP test feels like before you do it. Right now, the weekend I believe Miss Royce was looking at was April 9th. So if you want, I should be almost done, if not all the way done, teaching you by then, teaching you new material. So I'll get the details for that soon. But if anyone is interested in taking a mock exam, you okay? Sorry. You're good. Don't be sorry.
Only 2 hiccups.
All right. If anyone's interested in that, there's kind of 2 things that can happen there. Either you can realize what you need to study, or you can kind of realize that you're in a good spot going into the AP exam. It does not feel great, though. 3 hours of calculus, even for me, is a lot. So you want to see what that feels like. More details coming your way soon. All right, did I set this up right? Yes. But that's different than I'm going at a much slower pace, like explaining it, than I would actually when I was like testing it. Also, it's just a lot. All right. So you guys remember last time we started talking about antiderivatives? So we were starting to talk about like what thing would have this thing as a derivative. We found a new power rule that was adding 1 to the power and dividing by that new power instead of multiplying by our power and subtracting 1 like in derivatives. Trig was about representing or recognizing, different R word, recognizing the trig derivative that we had done before. So let's see if we can think about any of these ones. Sine x. The 2 can just hang around. What is the antiderivative of sine x? Negative cosine. I'd encourage you to bring that negative sign out in front of that too, so it doesn't look like we are subtracting. What should go at the end of all of our indefinite integrals? Plus c. That represents the constant that when we take the derivative kind of goes away. All right, so we have this power rule. It's kind of the only thing we can work with. So if we've got stuff like square root and 1 over x cubed, we're going to want to rewrite those first. When we rewrite, we're going to keep the integral symbol and the dx. What power could I write instead of, all right, perfect. Instead of square root is 1/2. All right, so what do we do to get the new power? We add 1. So it's 1/2 plus 1. 1.5, 3 halves, 3 halves. And then we could divide by the new power. So we could divide by 3 halves. But I think Evan last time was reminding us that we could also multiply by the reciprocal. So the number I would put here was 2/3. Was that you? Correct credit. All right. What am I missing? I'm making a big deal about that because I don't want to have to take off points for that. It's a really silly reason to lose points. All right. How do you think I'm going to rewrite 1 over x cubed? X to the negative 3. All right. Now, don't forget how to add 1 when there's negative exponents. What's the new power on this guy going to be? Negative 2, which means I'll divide by negative 2 or multiply it by negative 1/2. If you're feeling fancy and you want to start thinking about how these things could simplify for, say, a multiple choice question, remember your negative exponents bring you back down to the denominator. So I could do 1 over 2x squared plus c, that plus c just hanging at the end. All right. This one looks crazy. How could I rewrite it? I'll give you a hint. The 5 just stays. Yeah, the question is 4/3 or 3/4? 4/3. So you always have power on top and root on the bottom. That's going to be helpful. I'll throw my dx at the end. With coefficients like this 5, sometimes when the powers are getting a little bit weird, I like to just let the 5 linger out in front while I deal with the powers and then reintroduce it. What's the new power going to be on here? Good. 4/3 plus 3/3 is 7/3. Wow, the most confident I've heard fractions in a while. All right, what number is going to go out in front of that x? 3/7. We're going to multiply by the reciprocal. I'm going to add c at the end. Now, if I wanted to combo these numbers at the front, how could I do that? 15/7. Remember, you multiply across the top, across the bottom. If you need a bottom for the 5, it's over 1. Most of the time, I won't transfer these back into like this sort of notation, like the roots, because it's really not super helpful for solving or anything. You can if you want to. That would be like the cube root of x to the 7. All right, why does this last one look weird? Parentheses. What do the parentheses mean we're supposed to be doing? Multiplying. Do we have a product rule for integrals? No, not yet, and you won't this year until maybe after the AP test. It's something called integration by parts. That's not even a good method for this question anyway. So what do you think I'm going to do before I get started? Yeah, we're going to multiply this out. The bad acronym of FOIL, but I'm going to like double distribute this bad guy. So I'm going to have a 2x squared. Notice my integral symbol is still staying because I'm not necessarily integrating right now. I'm combining like terms. I got minus 10x and plus 1x, which I'm going to combine to give me minus 9x.
Hunger Games.
That's not Hunger Games. Last thing, minus 5 and a dx. While we're sitting here admiring the beautiful sounds coming from the bathroom, I would just like to take a second to say some people write integrals with parentheses around the integrand. Some textbooks, some teachers really prefer that. The way I got taught is that the integral symbol and the dx kind of act as parentheses. Both are acceptable, but if you're liking parentheses around your integrand, you can. All right, let's see if you remember anything. Take the next like 15 seconds to 30 seconds to try to integrate this on your own. You should end up with 4 things. Yeah. No, you can't do that.
She does it.
It's not right. Wait, why?
So you can tell what you're the variable you're in terms of immediately.
That's literally not correct. Physics teachers think they can just like change calculus.
He always tells us the name of something. He's like, I have to do this and something is this.
It's like I went to an AP institute, and you know all the polar graphs, like the lemniscate, whatever. He called the lemniscate lemon cake. And what's another one? He had another weird. The limaçon, you know, the lima bean. I was like, that's not even close. You just want another food thing. All right, anyone want to give me a first term? No? All right, 2/3 x cubed. What's next? All right, 9 has x squared. What comes next? Minus 5x. It's really tempting to want the constants to go away because when you took derivatives, they do, but they do not here. What am I missing? Perfect. All right. So we are going to continue practicing with this today. We're going to put some context over it of like, what does this mean? What does this help me do? And we're going to do a big connect back to area. So I'm going to give you a new set of notes. We're going to get part of the way through them. So I'll give it here and over here. And then we're going to take a solid break in the middle because there is a definite place we're breaking. What I would like you guys to do, the first few questions of this set of notes are just what we were talking about. So I'm just going to give you a couple minutes to try these. Get as far as you can. If you can get far, great. If you can only get a couple, that's also great. What?
Pretty complicated.
Just because I make it look grosser doesn't mean it's more complicated.
I'm serious. Stop. She took my notes. She took the notes.
I have extra ones if you want, dude. All
It's
right,
funny.
there's 6 problems. So let's try not 50 minutes. All right, you think you can get all of them done in 6 minutes? Minute per problem?
No.
Let's race. Let's see. Maybe. a couple, like the second one is gonna take you 10 seconds.
We'll see about that.
Are you sure?
It shouldn't even take you 10 seconds.
Are you sure?
Yes, I'm sure. I've been doing this for a while.
I don't know.
Are you questioning my credentials?
I'm thinking
Are you
I'm not,
challenging- are
maybe
you
like
challenging me to a math off?
98% sure. No. That would not be very
One of
smart.
my students did once. We were taking a practice AP test. He lost.
Really?
It
Yeah.
was a few years ago when I wasn't as practiced. He thought he was the coolest ever. He kept looking over, being like, "What question you on?" I was like 8. And he's like, "Oh, I'm on number 5." And then it was like, "What question you on?" I'm on 28. Oh, I'm on 15. I'm gonna stop asking now. Hello. We are just practicing some antiderivatives. Those stairs, man. You didn't need to rush. Thank you.
What the?
Which one?
These are really easy.
The first 4 should be pretty easy.
What?
I said the first 4 should be pretty easy.
Yeah, I have the first 4 done.
Good. I would,
The fifth one doesn't look hard. I think it's just gonna take a bit.
yeah, I would just try and pull all your numbers out front. So make it not look like a fraction anymore.
Okay.
And then think of rewriting your exponent like we did with one.
Back on top.
How do I get the 3 back on? Like the thirds?
Yeah.
I would just take the negative 5/3 and just push it out.
Oh.
Yeah, you're probably in a good place if the first 4 feel relatively comfortable right now.
What the heck?
Come on, man.
Ma'am.
For what you do with the number like in front of the X. Like I don't think.
I don't really know.
Like, that's the only one. Well, just like how do I find the number at the front?
So the problem is we compared to this is reading our first then decide.
So you're finding like a
Yeah. So think of like you want to reverse both processes from the derivative. So before we multiply by the number, then subtract one. You kind of want to think of that like
So just do the exponent
you
first.
want to do the exponent first. So we're reversing everything.
Okay.
The things are going.
And also while we're talking about like fractions,
Okay.
analogy.
I think I got it.
Yes.
I kind of wrote it.
I think that's right. Could you do those nice fractions?
Yeah. I didn't want to though, because if you cancel them, then it wouldn't end up equaling that.
It would.
It would?
You're not throwing
Well, it's not supposed to look like this. It's supposed to look like the antiderivative.
Oh, yeah.
All right, take about 2 more minutes, see what you can do.
Oh, yeah, you got it. Oh, I just, wait, is this correct? Well, not this one. Yeah, I should. So whenever we do it.
Oh, yeah.
No damsel?
Has everyone done 6 antiderivatives in
No,
6
almost
minutes?
done. Give me like 1 minute and 4 seconds.
Oh, okay. Exactly that.
Yeah.
I thought that was, I'm not sure about that one. No, Chris, I'm not sure about this. I'm not sure about
Is this not?
Right. I wrote it backwards.
Yeah.
I wrote it backwards. My bad. So wrong.
Well, you guys are very quiet though. Mentally preparing yourself for the last 30 seconds. I was waiting for racing the clock again. Are you racing the clock again?
Unnecessary.
Plus C.
Wow.
I told you. I called.
Wow. All right, so let's try to go over these, make sure we're in a good place, because this is one thing that will not go away. We're definitely going to be doing this all the rest of the year. So kind of like we subtracted one, took derivatives all the beginning of the year. Let's integrate. So you could be adding 1 to your power, 6, dividing by new power, and then adding C. Some of you have been simplifying already. Great. We're going to practice kind of without simplifying if you would like, but either one of those answers that I wrote up is perfectly fine and correct for right now. Eventually, we'll want to get simplifying those because we're going to be doing stuff with our antiderivatives, but either one is fine right now. Anyone want to volunteer something for this one? Thrilling. All right. Here you can see this. This one is typed out with parentheses around the integrand. Doesn't really change anything. This first term is kind of very similar to what we just did. Sadie made a good comment of, we were talking about like what order to do things in. She was noticing that you need to add to the power first, then divide, which is kind of different from derivatives where we multiplied first and then subtracted, kind of doing things opposite order. What's the new power on this second term going to be? Squared, divide by 2. Here, I'm going to simplify mine. Notice that the dx and the integral symbol go away when I'm doing this add 1, divide by new power. Thoughts on this one? Thoughts on the power? -2. Be careful with the negative powers. For some reason, people like to just not do them correctly. Here, you could either write x to the -2 plus c, or if you're feeling fancy, 1 over x squared. Whoa. Thrilling. How did you guys rewrite this one? All right, so split the 5/3 over here. X to what power? 2/3. Again, power over root. Don't drop that dx. Now, I'm going to keep the -5/3 just chilling right here. What will the new power on this be? So I like to, when I have more complicated powers going on, so usually any powers that are fractions, I like to just leave this guy for a hot second and then figure out what's going on. Did someone say the power for this guy? Is it 5/3? All right, adding 3/3. So what number should I put here? 3/5. So instead of dividing by 5/3, we're multiplying by the reciprocal. You could certainly leave it like this, but did anyone notice how cool this was? Thrilling. So -x to the 5/3 plus c. You could rewrite it back in your root, so that would be the cube root of x to the 5th. I don't like rewriting it like that, so I'm not going to. All right. Now, how did you guys rewrite the integrand on this guy? You can just fully close it. Perfect. All right. We are going to add 1 to the powers. Oops. Divide by new power. You can start, oops, I should probably add 1. You can start getting fancy and dividing right away. You don't have to write this middle step that I'm writing, but certainly doesn't hurt. You could also change these negative exponents back into things in the denominator. I'm just going to leave them because I ran out of room. All right, so we're going to do a couple examples of how we can kind of extend this thought process. The first one has to do with the plus C. So we'll do that, and maybe it will take, you guys want an early break today or a more midline break? Cool. All right, so we're going to do two things. The first one, a couple of words. We are actually finding what's called a general solution here. So all these guys with the plus C's, that is a general solution. Yep, we're leaving already. So why that's called a general solution is it's actually a bunch of different solutions depending on what the plus C is. So it's more a family of curves instead of just one specific curve. So for example, this one right here is all the lines that have a slope of -3, but could have different y-intercepts. A lot of the time, our plus C is just going to move our graph up and down, but we're going to get situations later on in the year where that plus C could be a stretch, a shrink, or something else. So this gives me a family of curves and not one specific curve. Well, what if I want to find the one specific curve that has this as its derivative, so has this thing as its slope, but also goes through a specific point? The fancy words for that is finding a particular solution with an initial condition. Those are like super huge words to say. I want to find a y equals without the plus C in it by plugging in a point, really. So I'm going to do one of these. You're going to do one to practice. Notice here we're given a differential equation, which is just we're given a derivative. And we're given a point here. This is kind of the new information, but this is what's called our initial condition. So we have a certain place where this graph should go up and down. All right. To get from a derivative back to a like y equals, well, if we took a derivative to get there, we should probably take an antiderivative to get back. So our y equals is going to be our integral of this function, our antiderivative. Cool. All right. Thoughts on the antiderivative of 3x squared minus 1? All right. X to the third, you would move the power up by 1 and then divide by new power. That would cancel that 3. And then minus x for the minus 1. Anything else? Plus c. Now that's going to become really important here. So we've got a family of curves. We want to figure out which curve is the one that goes through this specific point. So in my next set of steps, I'm going to plug in 2, 4. So I have 4 equals 2 cubed minus 2 plus c. Thrilling arithmetic. 2 cubed is 8. All right, so 4 is 6 plus c. So c is -2. All right, is my answer on the paper? No. So what the problem is our solution this time is not really a number. So it's not the c equals -2. Our solution now is a function that has this as the derivative and goes through the specific point. So we want to write x cubed minus x, and then instead of plus c, minus 2. So that's the graph that has that as its derivative. If you took the derivative, you get 3x squared minus 4. But if we graphed it, would also go through the point 2, 4. So what I'd like you guys to do is try the exact same thing, just with the function below. Notice I made it a little more interesting for you. Find me that plus c and write me my final function. And we're back. I was going to show you. Decimals. All right, so as you finish up, just kind of a visual of what we're doing, I guess. So in the first line, what I've graphed was our general solution for the first one and put a slider on that C. So notice as I move up and down, I kind of get to a perfect place where I go through that green dot. There's nothing on the screen. Wow, I was making a really cool point. I'm making a really cool point to the people who are watching.
I'm excited to see it when it shows up.
All right, well, when this shows up, it's going to be a Desmo screen that has our general solution in red that you will see moving up and down. Is it there now?
Yo, what the heck?
Cool. That green dot is our initial condition. So it's the one where we would like our graph to go through this. Every single graph of this has the same slope because it's just the same shape moving up and down. What did we get for C in this first one? -2, right? Wow, it goes through the dot. So let's try this with the second one. Hopefully we got similar things. How did you guys rewrite your function when you went to rewrite it to integrate? Perfect. I'm going to do that right away. And when I integrate, I'm going to add 1 to get -1. Dividing by -1, I usually just put a negative sign out front because I'm crafty. All right, now when I go to plug in this point, what point is this, by the way? 1, 0. A lot of people flip-flop those X's and Y's. This one would be particularly concerning if you flip-flop your X's and Y's because you'd be dividing by that 0, which is a little creepy. So I'm going to put the 0 in the Y. Did anyone rewrite their X to the -1? No. I guess you don't have to because it's a 1. Yeah, I did -1 over X. So then when I plugged in, I did get -1 over 1 plus C. So my C should be what? +1. All right. So my actual answer, -1 over X plus 1. Again, looking at that visual. Oh, I did not ask you to open. All right. We have -1 over X plus C. If our initial condition now 1, 0. So we want the graph that's going through that green point. We can kind of see it roll through there. If I change my C to be equal to 1, huzzah, we get through the right point. All right. So before we hit our break, I'm going to show you 2 questions of the fundamental theorem of calculus. Now, I will tell you that the proof of this is way beyond the scope of our class. So I'm going to need you to trust me that this is the thing that it is. This is how we are going to connect the things that we have been doing. So remember a couple of classes ago, we were talking about area under a curve. We had 2 ways to approximate it. Does anyone remember one of the ways we could approximate the area under a curve? Rectangles, which was Riemann sums, and then we used a different shape, trapezoids. Those are both approximations, and I said we would be learning the way to find the actual area under the curve. Now that's with something called the fundamental theorem of calculus. Now there is a reason I also taught you about antiderivatives, and that's because we need that to be able to find the area under the curve. So we're kind of connecting 2 ideas. We can either find area with, evaluate an integral with area, or we can do this process, and we're going to connect both of those today. So what we are going to do is a couple of things. If we integrate a function little f of x, and we have bounds from a to b, what this definition claims is that big F is the antiderivative of little f. So if we integrated this, if we did the antiderivative, we'd get big F of x. All right. we're going to use some notation to say, hey, I've taken the antiderivative, but hey, I haven't plugged in the bounds yet. What that notation is going to be is a vertical line. Some textbooks use like a bracket. I like the vertical line better, from A to B. And then really what the fundamental theorem of calculus says, I'm going to rewrite this left-hand side. So we're going to have to actually take the antiderivative of our function. Yes. So they're saying here that big F is the antiderivative of little f. And this is going to make a whole lot more sense once I do this first question. So just bear with me for a second. The actual fundamental theorem of calculus says I'm going to take my top bound, plug it in, and subtract my bottom bound when I plug it in. So we're going to practice this process 3 times, and then we're going to practice it in a little bit of context after we hit our break. So what does this actually look like when I do it? All right. I have my integral from 1 to 3 of x cubed dx. I'm going to first focus on the x cubed part. And I'm going to take the antiderivative just like we were taking on the front page. What's the new power of that x going to be? The 4th. And I will do a 1/4 out front to divide by that new power. Now that I have the antiderivative, I'm going to draw this vertical line and put my bounds on it. Does anyone notice something that's kind of missing here? The plus c, we're going to hit that in a second. It's supposed to be missing. All right. Now what I'm going to do is I'm going to plug in the top bound 3 and subtract when I plug in the bottom bound 1. Still no c. I will simplify. Anyone know what 3 to the 4th is? What? 81. Anyone know what 1 to the 4th is? It's 1. All right. 1 to the 4th? 1 times 1 times 1 times 1. Okay. All right. I'm going to do 81 minus 1 and then divide it by 4. So that's 80 over 4 or 20. So some questions. First of all, where the heck did the plus c go? Let's pretend I put the plus c over here. Notice that I would have plus c'd here, and then I would have plus c'd here. What's going to happen to that plus c since I'm subtracting? It's going to cancel, and it's going to cancel every single time. So we don't put it on there because we don't need it. So when we have bounds with our integral, we are not going to put plus c. Now, what does this number mean that I got? Let me draw you a picture. And by that, I mean graph in Desmos. You don't like my pictures? Wow. Y is less than x cubed. All right. And what were our bounds here? 1 to... What we found is we found the area between this curve and the x-axis between 1 and 3. Now, if you notice, this guy right here on the top, he is not a straight line. So I could not have done this with a trapezoid. I could not have done this with any of the math that I currently have in my toolbox. So this is a new problem that we're doing. We're able to find the area between the curve and the axis of something that is curvy.
Would it be 20-something squares?
Yeah, so if I had units on it, it could be like square feet, square meters. We're going to also look in context of, like, let's say the integrand is a rate of change. What kind of things would we do? So we'll add context as we go throughout this unit. For right now, what I want you to think of is that this number represents the area between my curve and the x-axis. Let's just practice this process a couple of more times so that we can see what's going on. So first things first, we are going to integrate the inside function. We're going to find an antiderivative. So 3x squared, what's that going to look like when I take the antiderivative? X to the 3rd. All right, we're going to add 1 to the power, divide by the new power, so we'll get x to the 3rd. All right. What about 2? 2x. All right. Will I do a plus c? No, I got bounds here, so I don't need it. If you do a plus c and they cancel, it's not the end of the world, but we're going to leave it off. All right. Now, the new part. Which bound goes in first? 2. The top bound always goes in first. So I'm going to do 2 cubed minus 2 times 2. Notice I'm using parentheses here. I'm subtracting multiple terms on the back end, so I really want to make sure I'm using my parentheses correctly. Now, you certainly could simplify more than I am in this moment in time. So this guy's going to be 8 minus 4, 1 minus 2. So here we said this is 4 minus -1, so 5. Yep, and kind of, it'll depend on what the units are of the thing that is my integrand. Again, we'll talk a lot. I'm going to have a whole unit that talks about, or a whole lesson about integrals in context. So we'll really talk about units there. In general, for right now, we're not going to be really giving any units for the answers to our questions, just because.
If one of the bounds is infinity, is the area just infinity?
Answer is it depends. We just learned about that in BC. Those are called improper integrals. So if you're interested in the answer to that question, sign up for BC next year. Excellent. All right, so this is the little area we found. Does 5 look like about right?
Yeah, it's like in the middle.
Yeah, it looks kind of almost like a triangle with a base of 1 and a height of 10. So it looks about right. That 5 should be about my answer. So you can kind of, you have some knowledge of graphs, you can get a little of a sanity check on what you think that answer will be. All right, let's do this last one real quick. Any thoughts on how I could rewrite my integrand? All right, I like making that square root into an x to the 1/2. All right, so as I go to integrate, I'm going to let the 3 chill for a second. What will the new power be on my x? 3/2. So number in front? 2/3. What'd you say, Herbie? Did you say something? Or was that Evan? Oh, does anyone notice anything cool? Does anyone notice these 3s? Yeah, so here we want to take advantage of some of the things we can do to simplify. So those 3s will cancel and I'll just have a coefficient of 2. So I've got 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Have we talked about how to evaluate something to the 3/2 cleanly yet? It's not very hard. All right. Good. So you can do this one of 2 ways. You can do 4 cubed and then square root it. That gets really hard, especially if things get bigger. What I would recommend is doing the square root of 4 cubed. So root first, then power. So that part would be 8. So I've got 2 times 8. 1's pretty easy though. That's just 2 times 1. So overall, minus 2, which is 14. So for like the 3/2, you would probably just leave it 5 to the 3/2 and you just, yeah. All right, one last little foray into our graphing just so you can see what's going on. X. And we are going from 1 to 4. All right, so that's our guy right there. Again, 14 looks about right. If I kind of rectangleized this thing, that's not a word, but whatever, that'd be 3 times 5 is about 15. So 14 looks about right. All right, let's take a solid break, and then we're going to lay some context on top of this, kind of connecting a little bit back to area, looking at some AP style problems. Let's do 5 minutes.
like my behavior after I put it in unknown shape.
What, Valerie?
You see my. You got the load in a little. I couldn't tell if you were gonna sneeze again.
I'm tired.
Really?
I have no excuse to be tired. It
We
was
can
just the
skip
weekend.
class if you wanted.
Yeah.
But I like this stuff. Integrals are so much cooler.
But you know what's even cooler is the sleep.
Yeah, but we're all here. I'm not sleeping in front of
I mean,
you.
we could all.
You're missing a quarter.
I would not be opposed to all of it.
Yeah, we're missing a quarter. We can take a break. We can watch a movie.
We can like
Watch a movie.
What kind of movies are there?
I can just connect my.
The one that I'm creating right now on my Google Meet. You guys are getting to watch the live performance though. How lucky.
No.
There aren't any. Yeah, we just pull up the Remon Songs video to review. These next questions are kind of cool though. The B one's really cool. I like that one. The one at the top of the next page. And then the one after that, also thrilling. The ones on the back page,
I got all of them for free.
intensely thrilling. I don't know how anyone can be team derivatives when integrals exist.
Basic derivatives seem a lot more.
What about the 5 9
Yeah, but who wants simple math?
It's going to be William Defoe.
Nah.
I think it's going to be William Adams.
Yeah, exactly.
What two
Sim-
first two additions to it's extremely.
I wonder why. I mean, I wonder what.
Yeah.
You literally
So that's all you need. You don't need subtraction. You don't need.
But who wants to read like Cat in the Hat when you could read like a better book?
Like, dude,
Why did you have the sixth one? Not so how much of a parabola, like, let me.
A parabola. No, we're here to answer interesting questions. BC is trying to answer the question.
Can you find the area of this lunchbox?
The area of it? He can find the volume of it.
Now the area.
The area? It's the surface area?
That's their.
Yeah, I think.
Sure, if he had a measuring device.
I would just like.
I would have for that thing, then yes.
Let's model it. Get it in GeoGebra.
Bruh, gotta go watch your dog. High five.
Actually, by the end of the year, I might be able to get you to find the volume of that cross section. Correct. This is geometry problem, really.
Yeah.
No, because then I wouldn't know what I was doing. I like to stick to one integral nowadays. I'm not smart enough. When it gets quiet.
Yes, Evan. Why? Because I was going fast. And also it's not on my hand. Oh no. So what to do?
Oh God.
Before school?
Yeah. I meant to take Dayquil, alright? I meant
Ooh,
to take Dayquil.
that's bold.
Bro, they're whole different colors. Right?
They're all
No, these ones are white. These ones
Oh,
are
okay.
Yeah.
Okay. The white one.
Generic.
I thought you took like the blue one.
No.
What?
No, these are the white ones.
All right. So what we're going to do now is we're going to roll through a bunch of different ways that the AP test can ask about integrals, hopefully getting to this back page where we're really going to combine all of the things that we've been talking about. I may skip around a little bit and we can revisit some of these at the beginning of next class or even the beginning of 2 classes from now, but I'm going to kind of get the most important stuff out of the way. So the amount of times that I'm just going to throw an integral at you and be like, do this, is not very often. Usually there's going to be some words that are telling you to do an integral. Looking at this question, what is the one big word that's really like shouting integral at us? Find the area. So area, just like slope told us about derivatives, area should make you start thinking about integrals. Now this says the area is bounded by the graph and the x-axis, which means I'm just going to straight up integrate this function. What are your thoughts on the bounds? Yeah, this 0 and this 2. Now sometimes I might be tasked with finding the bounds. I could graph it and see where it comes. Usually when we're in charge of setting them up, we're always going to put the bigger number on top and the smaller one at the bottom. That being said, that's a really good question because I don't necessarily have to set it up that way. So you might get an integral where they're switched. But if we set it up, especially if we're finding area, we're reading it like a graph. So smallest to largest, bottom to top. All right, I'm going to end my setup with dx. Let's see who was paying attention. I would like you guys, now that we set it up, to try to evaluate this integral. Apologies on the thirds. They're not going to cancel, but it's a good practice with fractions. So I'll start with about 3 minutes and I'll start putting up my work at the end of that. I would like one singular number at the end that should represent the area of the region bounded by my graph in the x-axis. Type in. Isn't it great?
That makes the last part really easy.
Yeah, so Herbie's noticing that the bottom bound being 0 is like really clutch. What? I didn't know calculus was so funny.
That is a funny fact.
I always think when people are laughing in class, they're laughing at me. Self-esteem issues.
No, I always tell you if I was laughing.
Thanks.
You make it fairly obvious if you're laughing.
You know, it's a scary thing to come up here and just like talk about stuff that you guys don't really want to know about all day. It's a bold sales pitch, really.
There are worse classes in this school.
Okay, I'll take that.
Like
I guess.
online class.
The worst.
They are terrible. I took one last year. I'm taking one this year.
To be fair, I didn't think I was the best teacher last year online. It didn't feel great.
No one was the best teacher last year.
I'm sure someone did it really well.
Mr. Deer.
Mr. Dearman's just like a fantastic teacher in general.
I got 100 in class. I don't know if it was really good.
All right, I hope my antiderivative is good because I'm about to start plugging stuff in. Wait, okay. I'll make a picture while I'm waiting. All right, if you've got an answer, you can kind of start comparing to the size of the shape, see if it makes sense. Notice he's very curvy. Hey, me too. All right, it doesn't look like anyone's doing anything anymore, so I'm gonna start to plug in. All right, so as you plug into your antiderivative, you can kind of be as thorough as you would like to be, I guess. So here I started simplifying as I was plugging in. So kind of got that 8, that 4 out of the way, the 2 times 2 out of the way. 16 thirds will be our 2 thirds times 8, minus 6 plus 4. I'm going to do these first. So minus 2, so that's minus 6 thirds. So I believe 10 thirds should be your final answer. So do notice that some arithmetic is coming back into play. We're going to practice with that, some like number talks at the beginning of class to get ourselves back in order. What? No, mixed numbers are gross. Those are only good, in my opinion, for baking. You could, if you wanted to compare sizes, I guess. So like, what is that, 3 1/3? So if you looked at this and you were like, yeah, 3 1/3 sounds about right. But we won't ever see them like that. All right, I would like to try 3 more questions. So I'm going to skip around a little bit. Now, this question I love. I've put it on so many different tests and quizzes and made new versions of this question because it is a great AP style question that's just like trust yourself. Trust that you know what you're going to have to do. And even if you don't see an end to the problem at the very beginning, just trust that you know what you're doing. So we've got an integral here. It's weird. It's got b's in it. Anyone freaked out? We shouldn't be. B is a constant. We can tell that because the numbers here, those are all numbers. They're constants. So I know that I can treat B just like a number. So we're going to do this integral, and we're going to hope that when we set this equal to 36 at the end, like it says, we're going to be able to solve for B. So for my first term, 4bx, when I integrate that, what's that going to look like? Let's see. Let's save the 4b. What new power is going to be on the x? 2. And I'm going to divide by that new power 2. Now the b gets to hang out because he's a constant. He's just like a 6, a 15. What? What do you mean separate them? Oh yeah, you could. Wait, what? 2b over 2? Yeah, I was just going to do 2bx squared in a second. Since everything's kind of being multiplied, I just need to divide them. All right. Now, 2x squared, that one's a little bit easier. How am I going to do that? Perfect. 2/3 x to the 3rd. All right. I have from 0 to b. I'm just going to drag this down really quick since I simplified. All right. So I've got this thing. What did we do next in all of our problems that we were doing? Plug in the bounds. Which one's going to go in first? B. All right, so I've got 2b times b squared. So that's 2b with 2 more b's, so 2b cubed. Minus 2/3 b cubed. All right, anyone excited about plugging in 0? All that's 0. Now, I want to tell you, I'm getting a little excited as we start to finish this problem because all my x's went away because I plugged in my bounds. So I just have b's. And not only that, I have 2 sets of b cubed. So I'm going to be able to combine those. Those are like terms. So what is, if I combine these, what is 2 minus 2/3? 4/3. Because I have 6/3 minus 2/3. Now, how am I going to be able to figure out what this is? Yeah, set this equal to 36. So I'm going to bring that equals 36 down here. Yep, I could multiply by 3/4 on both sides to get rid of the 4/3. Just like square rooting then cubing, I'd highly recommend dividing then multiplying. So I get b cubed equals 27, which means b is 3. So not a hard problem, but scary to look at. Let's do another example of that, and then we'll get one that is hard to look at and scary to do a little bit. All right, tables. I love tables. They're the greatest. This question, I could put on a BC test. Pretty much everyone's going to get it wrong, but it's the easiest thing out there. Because they would think it's too easy. All right. What do you think the antiderivative of f double prime is? F prime, right? An antiderivative undoes a derivative. So the antiderivative of f double prime, let's strip off of prime, f prime of x. I'm going to put my vertical bar on there because I haven't plugged in my bounds yet. Let's plug in the bounds. Which one goes in first? All right, hold on. Herbie's giving me some values. Let's check them and let's see. F prime of 3. I'm going to look at the F prime column, and I'm going to roll down to x equals 3. You guys agree with his 7? All right, this one, F prime of 1, 3. I get 4. Was that hard? No. All right. Yeah, that's literally all.
So they would somehow.
So they would get confused here. They would think it would be harder than that. So just, there are some things where the interaction with the table is the hard part. To scare you. Yeah. Extraneous information. Or it could be part of a larger free response problem where you're using different pieces of information in different things. So this could be one where, remember when we did like, oh, find the derivative of like f of g of x at a place. So I could be doing a bunch of those types of questions using one big table, but I only use pieces for different pieces. All right, I want to do one more set of questions and then I'm going to stop for today. This last thing that we're doing will probably be, will appear as a bonus on the questions for the quiz. So we worked with some graphs like this last time, right? All right. We are going to now connect the two ways we have to do integrals with bounds. This is going to be a little bit complicated, so I'm going to do one today, and we're going to let it kind of mellow in our brain a little bit, and I might open with the bottom one next time. Now, these are both questions off the AP test. How similar do those two graphs look? Kind of in the yeah, they have a very similar vibe. And I use this graph. We're going to see this graph a million times. I really like this graph. So let's read through the directions. I'm going to get just this top one done. It has 2 questions in it, but we're going to do the top ones here. So I've got this function. G is defined differentiable on the closed interval. We get a graph of its derivative though. So that's one thing to note. We are given the graph of its derivative and we are asked about the function G. So when I think of G of 3, I'm not just saying, oh, there's this point. I want the Y value. I'm looking for the Y value of a graph that I cannot currently see. We do have one interesting piece of information. And that is that G of 0 equals 5. So we know one singular point on the graph of G. Notice that does not match up with this one here because that's not the graph that we're looking at. All right, we would like to find 2 other points on this graph. I want to know what G of 3 is and G of -2. Now, those are 2 separate problems, so we're going to do this twice. All right. Not necessarily. We're going to make our own bounds here, but that is kind of the edges of our graph. So notice they're telling me that that's how far this graph goes. Also, things to confirm, they do tell me that those are line segments, so I don't have to assume anything about that. They do tell me that's a semicircle. So all of those things are just to confirm that what you're seeing in your picture is indeed what you're seeing. So I do like what Herbie's talking about with the bounds. Let's even backtrack a little bit more and talk about why we're going to need to integrate here. So thinking of the last question we just did, we want to go from G prime to G. Do you agree to remove that prime? An integral would probably be a good choice. I guess. All right, I'll take it. All right. Bounds are our next step. We are interested in kind of finding 2 places, one that we know about and one that we care about. Does anyone see a good X value? So we're going to work on G of 3 first. All right. I like 3. I don't necessarily like 5. I think X values. -2 will be for the next one. What is an X value where we already do know the Y value? 0. Yes, so we're going to do two different problems. So you're going to see this twice. And it's got a slightly different orientation, kind of going back to one of Satya's questions from earlier. So we're going to focus now on G of 3. So I'm going to use the bound that I know about, which is G of 0. So I know about x equals 0. And the bound that I'm trying to find, which is x equals 3. Going back to Satya's question from earlier, which one am I going to put on the bottom if I'm going between x equals 0 and x equals 3? The smaller one. So I'm going to go 0 and 3. All right, let's kind of follow through with what we've been doing today. What is the antiderivative of g prime of x? G of x from 0 to 3, and I'm going to plug in my bounds. So I have g of, which one comes first? 3 minus g of 0. All right, so let's talk about how to find these things. We've got a lot that we want to find in this question. This is going to connect a lot of the things we've done. So this is going to connect literally everything we've done this unit. So what is the thing we're actually looking to solve for? G of 3. That's the thing I actually want to find in this question. That's a little confusing because we've been finding some integrals. So I have to figure out something else to do here. All right, G of 0, we were told in the question, right? So I'm going to replace that. That guy was given in the question. All right. Now I need to find a way to put something on the left-hand side of this equation that has to do with this integral. But I have a graph. What does an integral mean on a graph? So when I ask you that question about derivatives, what does a derivative mean on a graph? You usually answered slope. What does an integral mean on a graph? The what? Okay. The area would be what we're talking about. I like the idea of anti-slope. Let's go with area. So we're connecting now not only this fundamental theorem of calculus, but the idea that an integral means area. Now, looking between 0 and 3, do we need calculus to find this area? Do we need to be able to find an antiderivative and plug in bounds? No, I think those are geometric shapes we can actually find. So to evaluate the left-hand side of this equation, we're going to find the areas of those shapes. This first shape, what is that? A quarter circle, so like pi over 4r squared. What is the r of that semicircle? Quarter circle. 2. All right. We have another shape. How thrilling. What's the other shape? A triangle. What's that? 1/2 base times height? Thanks, Sergey. And the height, I think, is 3. Thanks for labeling that point, AP people. Now, to solve for G of 3, I can do a little bit of simplifying on the left-hand side, and I can add that 5 over to the right. So I'm actually not going to do very much simplifying at all. This was a free response, so literally as soon as I move that 5, I'm really done. This guy is pi over 4 times 4, so that's pi. All of those numbers from the triangle are 3/2, and I'm going to add my 5, and I can be done. But what? What do you mean other side? Oh yeah, we're gonna do that. Sorry. All right, so just focusing on doing this process one more time. Notice this question did have 2 pieces to it. So I'm gonna do this question again, just with the -2 now. You could if you wanted to. On the AP test, this was a free response question, so I could have literally left it like this plus 5 if I wanted to. You don't have to simplify as soon as you can like put it in the calculator. All right. So again, if I'm finding G of -2, and then I'm going to shut up for today, I need to have a bound that I know about. So a bound that I can plug it into G and get a number, and a bound that I care about. I would venture to say this time the bound I care about is -2. All right, hold. What is the bound that I can plug in to G right now? I can do 0. Technically, I could use 3 as well because I just found it, but 3 is farther away from -2. So let's go with -2 and 0. Which one do I want to put on the bottom of my -2? All right. Now, if you want to start not writing this middle step that I've been writing, this guy right here, the g of x, when you integrate, you can. I'm going to write it here just to really emphasize. The antiderivative of g prime is g, and I'm going from -2 to 0, which will give me g of 0 minus g of -2. So notice our orientation of the one we're solving for is a little bit different. Not too scary, though. All right. So g of -2 is the one that I'm looking for. What was g of 0 again? 5, and that was given in the question. How am I going to do this integral part? Area. So let's look between -2 and 0. Yeah. Okay, so we're doing the other quarter circle here. You could do pi over 4 times 2 squared again, but it's just pi. So I have pi equals 5 minus g of -2. Yeah, what do we get? Perfect. For up here. So one thing you can do if you want is to evaluate these areas on the graph. Would you agree with me, Sachi, that this is a quarter of a circle, that yellow part? So I'm taking pi r squared and dividing it by 4 since I only want a quarter of it. The radius of that guy is 1, 2, or 1, 2, however you count. What is this? Y? 4? Oh. No. So that's this triangle right here. So this is 1/2 base times height. Base is 1, height is 3, coming from this right here. Okay, so you can find the area of these shapes on your graph if you'd like, or you can find them in here. All right, how are we feeling about some of these questions? So some updates for you. We are probably going to practice with this a little bit more next time. If you're feeling spicy at the end of today's class and want to try the bottom one, we'll definitely go over that one at the beginning of next class. But to give you some practice on a little bit of the easier questions, aka the antiderivatives that we've been doing since last class, and at least one where you're plugging in the bounds, we have a notes check. I was a little lazy and only made one version. So check your neighbor's numbers, check your neighbor's notation. You guys have 4 questions between you and the end of class today. I want this before you leave. All right, so the first 2 do not have bounds, so they do have plus C. The last 2 do have bounds, so your answer should be a number. Oh yeah, you guys are taking your SOL soon. Everyone. Oh, is Johnny jumping tonight?